Hello, folks. Dr. Matt Moynihan here. I wanted to do a special video on the Dynamac. I was just looking on YouTube, and I don't think I see anything that's a very complete explanation of how the Dynamac works. It's also a very novel and unique fusion approach. It's kind of different from the other magnetic confinement approaches, so I think it deserves its own video. Always, you can check out the other lectures that I have up on YouTube, and the link should be set below. So let's look at the history of this machine, because it actually dates back about 50 years to the early 1970s. At the beginning, it was just a theoretical concept. It was first laid out by a physicist named John B. Taylor in England. He was a British physicist, and he was a theoretician. And he showed that if you put plasma in excited state, basically spin up plasma, and you allow that plasma to minimize its total energy and conserve its helicity. So what is helicity? Helicity is a measure of twist in a magnetic field. And so in this scenario, the plasma has its own magnetic field that it's generated, and the plasma and the magnetic field go hand in hand. They're basically embedded together. The plasma is magnetized, if you want to use that word. So if you spin up a plasma like this and you allow it to conserve its helicity, but also minimize its energy, Taylor showed that there will be something called the Taylor state that will form. Basically, the plasma will self-structure naturally. It will form this natural plasma structure that he called the Taylor state. And there are actually two machines that exhibit Taylor states in real life. One of them, of course, is the Dynamac, but the other one is a reverse field pinch, an RFP, which is also kind of a unique fusion approach. It's studied at the Madison Symmetric Torus out in University of Wisconsin-Madison, and it has been for about 25 years. But so both of those machines exhibit Taylor states, and Taylor states are natural plasma structures that form inside an excited cloud of plasma when the plasma is allowed to conserve its helicity, so its magnetic twist, and minimize its energy. So Taylor showed this with some math equations. He also had some limited evidence from the zeta pinch being studied experimentally in England at the time that he wrote the paper. So he had some experimental evidence to point to, but we didn't really have at that time in the early 1970s. The paper came out in 1974. Nobody had actually experimented really with this thing and knew that it existed, at least on paper, but understanding it was a whole other effort. So shortly thereafter, the United States wanted to test this, and a team at Los Alamos proposed an experiment to kind of prove out this Taylor state theory and kind of get a feel for what it looked like in practice. And so they proposed this approach, this machine called the compact toroid experiment, the CTX, which operated at Los Alamos from 1978 to 1987, roughly. And it was a pretty crude first pass at how you form these plasma structures. Now, the plasma structure that's formed, I should say, just to go back, in a Dynamac is called a spheromac. So Dynamac, by definition, is a spheromac that is formed using continuous magnetic induction injection, magnetic helicity injection. Formed and heated and sustained. Spheromac looks like a twisted donut. It's very similar to the plasma structure you see inside a tokamak. Have you ever seen models of a tokamak? Hopefully I'm showing a model of a tokamak right now. And you can see this kind of a twisted plasma ring where the plasma goes around in a circle, but it also twists around the ring as it does so. That is the spheromac, but in the case of the spheromac, that is forming naturally. That is forming through a natural relaxation process. And that is called a Taylor state. In the case of a tokamak, it's sort of a forced thing. Is a more extreme version of this where the magnets themselves are twisted up and oddly shaped to create this twisted shape. So the bottom line is the shape is kind of universal, whether it's a Spheromak, a tokamak, or a stellarator. They're all trying to make these twisted donuts of plasma around a ring. But in the Dynamak, it forms naturally. Now, that natural formation process gives it several advantages that supporters argue will really help it when compared to a tokamak. Help it succeed because it makes the machine simpler, it makes it smaller, because it forms naturally, it's not prone to instabilities. Because it forms naturally, it allows you to pump in a lot of heat, energy, and plasma density, and you can reach past, you can reach up to the limit. The Mercer limit is the actual term. In any case, let's jump back to the 1980s. So Los Alamos runs this experiment called CTX. And as I said, it was a crude first example of testing out this machine. It formed the Spheromak, basically a plasma donut, in a plasma injector. It then pushed that donut out into an open space and allowed it to fill a metal cage, basically a copper cage. Now, in this machine's case, the plasma itself is self-generating a magnetic field. That is known. When you push it into the metal cage, which I'm hopefully showing a picture of, the field by the plasma extends into the cage, which is why the cage is made of copper. It's a conductor. So, and this is used, this extension into the cage is important because it allows the flux to kind of be stable while that plasma structure forms on the inside. This is an important distinction that the Dynamak is going to have with a tokamak, a mirror, and other conventional approaches. The field itself that sustains the structure extends into the cage, which means that the plasma has to be really close to the wall, and that opens up a variety of problems, first wall interactions, arcing, and other issues. So results on the CTX were good, and that prompted follow-on experiments at Livermore at a machine called the Sustained Spheromak Physics Experiment, or SSPX. This was at Livermore, operating roughly from 1999 to 2007. This machine was bigger than CTX, and it also had a lot more diagnostics, and it formed the plasma object in a much better way. So it's basically a beefier, larger, stooped up improvement over the previous CTX. And by this time we had learned a lot, and so this new machine had a little bit of different characteristics. But the SSPX would form a plasma ring, a plasma structure in the back of the thing. And then it would push the structure forward into a chamber. So SSPX was a good way to study naturally forming plasma structures, these smoke ring or donuts, if you want to call them that formed after being spit out of a plasma cannon. Now, CTX was championed by Thomas Jarboe, who joined Los Alamos in 1974, right after he finished grad school, and was with them until he moved to the University of Washington in the mid to early 1990s. He fell in love. He was attached to this approach and eventually became one of the leading advocates for it and one of the leading experimentalists on it. When he moved to the University of Washington after CTX was shut down and after some years at Los Alamos, he took up a position as associate professor and eventually full professor. Tom Jarboe became the lead experimentalist for a machine called Helicity Injected Torus, or HIT, which was the first version of a series of machines which will be built at the University of Washington starting in the late 1990s. The HIT approach was to basically prove out that if you added continuous induction. So you created a field that continuously was induced inside the plasma and the walls of the reactor. You could start, heat, and sustain these plasma structures in the right kind of chamber. So he worked on that. HIT was eventually HIT-SI. So they added a hyphen and the words steady induction, inductive drive, 2004 to 2012, roughly. This steady induction approach was tested. Tom Jarboe was running that machine as well. In 2011, the team published essentially what is a major breakthrough in the development and sustainment of these machines. They showed that inductive drive, where you create magnetic flux and twist in the magnetic field, would filter from injectors down into the main chamber and then drive the plasma structure. And so what that meant was you could continuously do that, and you could spin up a plasma, a Sphermac that's hot and dense, and then maintain it using continuous magnetic flux generation inside the chamber itself and the surrounding walls. So that was a landmark paper that came out in 2011, and that was one of the first times that Jarboe named the dynamo drive. It had a different name at the time, steady helicity injection, SHI. And that's mentioned in some of the papers. Of course, that language has sort of been dropped now, but after that paper in 2011, it was the first time that the group could really foresee a path to a commercial fusion power plant built off of this. And in 2014, Derek Sutherland, who is Tom Jarboe's essentially his protege, he was his advisor, published a paper called the Dynamac, specifically in the Journal of Fusion Engineering, which laid out what a power plant based around this concept would look like. And so now that group has spun out into CT Fusion, which is a private fusion company. They've raised an ARPA-E award, and they are pursuing the Dynamac as an approach to nuclear fusion. Just want to add one more thread to this. Outside of Tom Jarboe, Dr. Paul Bellin, who is at Caltech, so Berkeley, is also a champion for these approaches. And he built his own machine, the Caltech Sphermac experiment, so CSX, in the late 90s, early 2000s. For about a decade, that machine was running. Tests were being done, graduate students were graduating, and PhD theses were being written around that machine. So that and Paul Bellin wrote a really good book on plasma structures that includes the Dynamac and CT Fusion, although he probably wouldn't have the right term for it at that time because the term Dynamac wasn't in existence in 2000. But that book is a really nice overview of all these technologies, and it shows how passionate he was about trying to turn this into a commercially viable power plant. Anyway, the Dynamac, a modern Dynamac works by having a plasma inside a very oddly shaped chamber. There should be a picture of it on the screen. And you start by driving a magnetic induction into the plasma. So the plasma is sitting there, it's all there, and it's interacting electrostatically, and it's got some magnetic fields in play because of the plasma motion generates magnetic fields. But what you do when you start it is you wrap a alternating current coil around these injectors, and you run the current, and that, because of Faraday's law of induction, only a changing electric field will create a magnetic field. The same principle is used in a transformer. In a transformer, the primary loop is driven by an alternating current, and that generates a magnetic flux that travels through the transformer and induces a current on the secondary side. So in that respect, the Dynamac is kind of using similar principles to a transformer. It's also very novel for a fusion reactor concept. Most fusion magnetic confinement schemes do not have changing fields like this because it introduces plasma instabilities. However, in the case of the Dynamac, it actually is needed to drive the machine to work. You apply this alternating current around the inductors, which kind of look like handles on a teacup, if you can think of them. Hopefully I'm showing a picture of this. That induction, that alternating current creates an induced field in the chamber and in the walls, in the copper covered walls, which means which has implications for this reactor, which I just discussed. That flux basically travels into the center chamber, and the helicity relaxation process occurs, the process that Taylor laid out, I'm now describing. So the chaotic plasma is now moving. The field lines are all kind of they're all forming. And then when the system relaxes, the plasma structure has formed in the center. The field lines have all calmed down. And you can see the formation of the plasma structure there. Now, that relaxation process, there are rules on that process, of course, like anything else. There are operating windows where if you ran the machine in those operating windows, it would fail. So you got to do this correctly, and you got to run it the right way. So the Dynamac is sustained using this injection method, and the three injectors are offset from one another. So in the case of the three injectors, they're off by about 60 degrees. So one is peaking while the other two are in decline or coming up. And as a consequence, they never peak together. And the plasma sees a field that is constantly changing, but far away, and then close up to where the plasma structure is forming, that plasma is relaxing its field and forming this plasma donut that looks an awful lot like a tokamak. Material inside is hotter, denser, and better because of that. So I'll just close with a discussion of the advantages that the Dynamac presents, at least the supporters argue that it presents. The first and foremost is that the natural formation of the Taylor state and the Spheromac means that it's naturally not prone to instabilities. Because it's forming naturally, there aren't these heavy laden instabilities that could form here. So it's more stable from that respect. The fact that you can heat and sustain material with this injection method is very novel. It means that you don't need neutral beam injection. It also means that your equipment can be far away from the plasma, which is good for a variety of engineering reasons. If you're building a power plant out of this thing, you'd want room around it to kind of extract the neutrons or to extract the heat, et cetera, et cetera. The supporters, probably the biggest thing is that supporters argue that this helicity injection method is 2 to 3 orders of magnitude more efficient than, say, neutral beam injection, which is common for fusion experiments. That claim, I don't know if it's been backed up by evidence. I mean, I think it's mostly a theoretical math type argument. But I'd like to see some evidence, probably from the CT Fusion team, that shows that this helicity injection method is significantly more efficient for heating plasma than a neutral beam injection or some other method. Similar approaches, a magnetic oscillation approach was actually patented by Lockheed Martin, for example. So there are other places in the fusion field where this kind of thing exists, and it'd be nice to compare notes with the Dynamac and some other approach, notably Lockheed, for how this would work in practice. And because of this natural formation process and this lack of instabilities, supporters have also argued that allows them to get to near the Mercer limit. So basically, densify and pressurize your plasma up past a limit that was hampering tokamaks. So basically, it was discovered for tokamaks. Again, I don't know if there is sufficient evidence to show that this is a true or false statement. It seems likely that this natural formation process would reduce the instabilities, but I've seen a lot of models go awry when you actually try to do stuff in person. So I'd say, let's see it in person, or let's see a paper with raw data extracted from it. Regardless, this is a very novel approach to fusion, and it has a lot of unique characteristics. It has some drawbacks. As I mentioned, the induction in the walls kind of means that the plasma always has to be facing the wall. So you have this plasma material interaction issue that's going to be pretty prevalent in the Dynamac. But other than that, very unique approach from plasma physics perspective. Okay, thank you so much. Have a nice day. Bye.